Okay, dynamics part 1. Okay, in this part, we will be covering Newton's law of motion. There are 3 Newton's law of motion. We'll be covering all 3 of them. Okay, so these are the learning outcomes. We'll be covering Newton's first law, second law, and third law. Okay, so in lower sec science, we have actually learned that a force is a push or a pull. We cannot see a force, but we can feel the effect of a force. So some of the examples of effects of forces are a force can cause a stationary object to start moving. It can increase the speed of a moving object or decrease the speed of a moving object, and it can also change the direction of a moving object. So, based on the 4 effects of forces, we can see that when a force is applied to an object, it causes a change in its velocity, either start moving, stop moving, change direction, increase speed, or decrease speed. So we say that a force can cause an object to accelerate or decelerate because of this change in velocity. Okay, but a question comes. So if an object has 0 acceleration, it is stationary or moving with a constant velocity, does it mean that there are no forces acting on it? The answer is no. There might be forces still acting on it, just that the resultant or net force is 0. So to understand more about resultant or net force, we move on into a few examples. Over here, we have box ABC, and we have a few forces acting on these boxes. Okay, so in A, I have 2 newtons and 3 newtons acting in the same direction. So the resultant force is like an overall. The net force acting on A is the result of both forces acting on it. So the overall force acting on box A will be 5 newtons to the right. And 3 and 2 newtons acting on in opposite direction on B, it will result in a resultant force of 1 newton to the right of B. And for C, 3 newtons and 3 newtons acting in opposite direction, we say that box C actually has 0 resultant force. It doesn't mean that there are no forces acting on C at all. There are forces acting on C, which is 3 newtons and 3 newtons, just that they are in opposite direction. So we say that box C has 0 resultant force. Okay, so to test your understanding, let's look at this question. You may pause the video to think of the answers. Okay, let's go through. We say that the resultant force acting on this box is 0 Newton. So what is a possible value for R? Okay, so we can see on the left-hand side, I have a total of 10 plus 40, which is 50 newtons. And on the right-hand side, in order to have 0 resultant force acting on it, my right-hand side must also be 50. So the answer should be, R should be 20 newtons. 30 plus 20 will give you 50 newtons. Okay, so whenever we say that the resultant force acting on an object is 0, we say that the forces acting on the object are balanced. All the forces are balanced. Then it comes to Newton's first law. Newton's first law of motion states that object will either continue its state of rest or uniform motion in a straight line with a constant speed unless there is a resultant force acting on it. So Newton's first law is mostly talking about when there is 0 resultant force. Object will have no acceleration, no deceleration, or we say it has 0 acceleration, which means that it either moving at constant speed or not moving at all, depending on its original motion. Okay, so you can take a look at an example over here. You have a table. So the table is stationary. A book. You have a book on the table. So the book is stationary on the table. So what happens is, it doesn't mean that there are no forces acting on the book at all. We know that there must definitely be a weight pulling down on the book. Okay, but it is simply balanced by the contact force acting on the book. Okay, so there is a weight downwards, and the table, since the book is in contact with the table, there is a contact force exerted by the table on the book. And this contact force is exerted upwards and is equal in magnitude to the weight. So the two forces acting on the book are equal in magnitude, but in opposite direction. So there is actually no net force acting on this book at all. Okay, so this book will remain at rest because its original motion is already at rest. Okay, then let's take a look at another example. I have a book sliding across a table. So this book original motion is not at rest, it's already moving. Okay, it's sliding along the table. So as you slide, okay, I exert a forward force, pushing force to move this book to slide across the table. But as I slide across the table, there is also another force called friction between the table and the book. Okay, so the friction acts in the opposite direction to the pushing force. So when this book moves at constant velocity, again, it means that it has no acceleration. It's not moving faster and faster. It has zero acceleration. So when it has zero acceleration, or when it's moving with constant velocity, we say that the resultant force is zero. Doesn't mean that there are no forces. There are forces. There's the pushing force and there's the friction. Just that the pushing force and the frictional force are equal and in opposite directions. So the forces acting on this book is balanced. Okay, there is zero resultant force acting on this book. Okay, so, and I give you more examples. So you have a car stationary at rest on the road, moving with 0 meter per second, not moving at all. We say that, is there any forces acting on it? No, there is no forces acting on it. Okay, maybe there is a weight and a contact force, but there is no horizontal force acting on it. So we say that the horizontal force acting on this car is actually 0. The resultant horizontal force is 0 Newton. And then I have another car over here is moving with a constant velocity. Okay, constant velocity 2 meters per second. Okay, so if I'm moving with a constant velocity, are there any horizontal force acting on it? Yes, there is horizontal force. There must be a driving force forward to move the car forward. And at the same time, I cannot only have a driving force, because if I only have a driving force, then I would have a resultant force acting on this car. But I know that in order for this car to move with constant velocity, I must have 0 resultant force. So there's actually another force acting on this car backwards, which is the frictional force. So the driving force and the frictional force are actually equal. So the forces are balanced, and the resultant force acting on this car is again 0. That's why this car is moving with constant velocity. Okay, so now let's test your understanding. You may pause the video to think of the answers. I'm going to go through the answers now. A boy is pushing a box at a constant speed on a straight line, okay, on a straight path. What statement describes the horizontal force acting on the box? Okay, so the keyword is constant speed. So we know that if something is having constant speed, it means that there is 0 acceleration. 0 acceleration means that the resultant force is 0. So I need to think in the line of the resultant force is 0. How can the resultant force be 0 when a boy is already pushing on the box? So it cannot be there are no horizontal force. Okay, so there must be a pushing force. So the only one is when the pushing force is balanced with the frictional force. So the answer should be A. Okay, next question. A hockey puck lies at rest on a perfectly smooth surface. Perfectly smooth surface means that there is no friction at all. So you give the hockey puck a quick push. So only at the start you give it a push. Okay, so the force acting on the hockey puck is momentarily, only at the instant. The push doesn't last continuously, only at the start. You push it, then the force is being removed. Describe the subsequent motion of the hockey puck. So once you give it a push, the hockey puck is set in motion. So the hockey puck is now moving. And then you remove this pushing force. Okay, so now there is no friction, there is no pushing force. Okay, this hockey puck has no other forces acting on it, and its original motion is already moving. So the answer is it will continue to move with a constant speed in a straight line. Okay, because there are no net force acting on this hockey puck along its motion. There's no friction, there's no pushing force, and it's already moving. So it will continue to move at a constant speed. Okay, next. So we come back to Newton's first law again. It's linked to something called inertia. Okay, so you have a scenario over here. Imagine that you are being chased by a charging elephant while on a safari in Africa. To escape the charging elephant, should you run in a straight line or in a zigzag manner, as shown in the picture? Okay, so in order to escape from this charging elephant, we need to understand what is inertia and how is it related to mass. Okay, so inertia is linked to Newton's first law. Okay, Newton's first law says that objects don't like to change its state of rest. or its motion unless there is a resultant force. Okay, so this reluctance of this object to change its state of rest or motion is actually called inertia. Okay, I don't like to change my motion or my state of rest. Okay, and this inertia is dependent on mass. Okay, an object with greater mass will have a greater inertia. It's only dependent on mass. It doesn't depend on the initial speed or the initial motion. It is only dependent on mass. So what does it mean? It means that the larger the mass, the harder it is to start moving, slow down, stop moving, move faster, or to change direction. Okay, so comparing an elephant and you, the elephant has a much larger mass. Okay, it is very hard. Okay, there's a very great reluctance for this elephant to change its state of motion, which is running. Okay, so it is easier for an elephant to run in a straight line as compared to running in zigzag manner, because in zigzag manner he has to change his direction, and due to his mass it's very hard for him to change his direction as compared to you. You have a smaller mass, it is easier for you to run in a zigzag manner compared to the elephant. So in order to escape from the elephant, you should run in a zigzag manner. Okay, let's go into more examples. Okay. Belts. Okay, why do we need to wear seat belts? Because the car is originally moving. So if you do not wear seat belt and the driver suddenly applies the brake, okay, your body will still your body is reluctant to stop. Okay, it want to continue its motion because your body is moving together with the car at a certain speed. So when you suddenly apply the brake, the body want to continue moving forward. Okay, your body doesn't want to stop. That is the reason why you will lurch forward when the driver suddenly apply the brake. And the seatbelt is meant to prevent injuries when you lurch forward. Okay, I have more examples. If you spin a raw egg and a hard-boiled egg, which one will stop first when you touch it? Video now.
Most people know that if you try to spin a boiled egg, it'll spin nicely. And when you try to spin a raw egg, it'll be a bit more wobbly. But there's a cool trick you can do where if you spin a raw egg and then you stop it, the raw egg will start spinning again. What's going on? Why does it keep spinning? Well, it's because of something pretty important to physics, which is called inertia. Inertia is the property that all objects have, which keeps them doing what they're doing. So when you get the egg spinning, the yolk inside is spinning as well. And if you stop it from the outside, if you stop the shell, the yolk keeps spinning inside. So it'll get the egg spinning again without you having to touch it. Whereas with a hard-boiled egg, because the thing is solid inside, because the egg is solid, as soon as you stop the shell, you stop the whole egg, and there is no more inertia to keep the egg spinning.
Okay, it is also the reason why hard-boiled egg is harder to start spinning at the start. Okay, because it doesn't want to change its original state of rest. Okay, but for your raw egg, because the liquid is moving, so it's easier for it to change. Next, let's move on. Okay, then we move on to what happens when there's unbalanced force. We know that it's not always the case where there is always balanced force and an object will move with zero acceleration. There are some cases where it will be a resultant force. Okay, the forces are not balanced and there will be a resultant force. So for example, over here, okay, if the pushing force, there is a pushing force that pushes this book along the table. What happens if the pushing force is larger than the friction? So now the forces are unbalanced. There will be a resultant force to the right. Okay, and what happens when the pushing force is being removed? Okay, so push the book starts sliding, and then you remove the pushing force, there will still be a friction because the book is still moving. So the only force now is the friction. So there is a resultant force acting on this book. So whenever the forces are unbalanced, or whenever there is a resultant force, we apply Newton's second law of motion, which states that when a resultant force acts on an object, the object will accelerate in the direction of the resultant force. So whenever there is a resultant force, the object will not have zero acceleration. The object will accelerate. Okay, and the direction of the acceleration will be the same as the direction of the resultant force. So objects can either accelerate or decelerate depending on the direction. Okay, so there is a formula for calculating the resultant force. Okay, so resultant force F equals to ma, whereby m is the mass in kg and a is the acceleration of the object. So whenever there is a resultant force, there will be an acceleration. And when there is no acceleration, acceleration is zero, constant speed or not moving, resultant force will be zero. We say that the forces are balanced. That is first law. Okay, so let's take a look at this example. So the same car now I have, but this same car now is not moving with constant speed. It's moving with a constant acceleration of 2 meters per second squared. So what does it mean? If I am moving with a constant acceleration, I must have forces acting on it. I must have a driving force forward and a frictional force backwards. And in this case, the driving force and frictional force will not be balanced. If I'm balanced, I will not have an acceleration. But since I am accelerating to the right, my driving force must be greater than the frictional force. So I do have a resultant force. And the car will accelerate in the direction of the resultant force. Okay, next example, but friction exists in the real world. If you give a box a push, in order to get the box to start acceleration, your push must be greater than the friction. Then there will be a resultant force because the forces are unbalanced, and the box will start to accelerate in the forward direction of the push. Okay, and then, but what happens, okay, if the push force is removed, then there is only friction acting on it. Okay, so now there is again unbalanced force, which is I'm left with the friction. Friction becomes my resultant force. But the box is, so if the box is moving to the right, okay, the direction of motion of the box is to the right. But now my resultant force is to the left. And by Newton's second law, I know that if my resultant force is to the left, my acceleration will also be to the left. Okay, but it doesn't mean that acceleration to the left, it doesn't mean that the box is moving to the left, because the box is still moving to the right based on the initial push. That is my original motion. I cannot suddenly change direction. Okay, so my original motion is to the right. This box will continue to move to the right, but my acceleration is to the left now because resultant force is to the left. So if the box acceleration is to the left, then in the direction of to the right, it will be decelerating, opposite. Accelerating to the left means decelerating to the right. Okay, so what does it mean? It means that this box will decelerate because this box is moving to the right. It decelerates means it slows down. Eventually, it will stop moving. Okay, because of friction. Okay, let's take a look at more examples. A car of mass 1000 kg travels on a smooth road at a constant velocity of 50 kilometers per hour. It experiences an engine force of 5,000 newtons. What is the resultant force? So I've already bold for you. The keywords is moving with a constant velocity. So you should know that constant velocity simply means zero acceleration. And when you have zero acceleration, it means that it has zero resultant force. Okay, next. So now the same car of 1000 kg, now it doesn't move with a constant velocity. It has an acceleration. it accelerates from rest to 20 meters per second in 5 seconds. So now I have an acceleration. I know that I must have a resultant force. The forces must be unbalanced in order to create this acceleration. So how much is the resultant force? I know that there is a formula for calculation of resultant force, F equals to ma. Okay, I have the mass, but I need to calculate the acceleration. So the acceleration is not 20, this is the speed. Okay, the final speed from rest to 20 meters per second. So the first step I need to do is I need to calculate the acceleration. Acceleration is v minus u over t. Final speed 20 minus starting speed, which is at rest 0 over 5 seconds. So this car is moving with a constant acceleration of 4 meters per second square. And then I can proceed to find my resultant force using the formula F equals to ma. 1000 kg times 4 meters per second square, I get 4000 Newton. That is my resultant force acting on this car. Okay, then there is another formula that I'm going to introduce to you in this part. The same car with the same acceleration of 4 meters per second. Okay, but in this case, in the previous example, I'm calculating the resultant force that acts on this car. So there is a resultant force of 4000 newtons. But you take a look at this example. I'm not interested in finding the resultant force. I am interested in finding the driving force, which is one out of the two forces that acts on the car. So on the car, there's a driving force and there is a friction that acts backwards to give my resultant force. So there is another formula that you need to know is resultant force is always equals to the forward force minus the backwards force. As long as the question asks for a certain force, or in the question there is a certain force that is not labeled as the resultant force or the net force, you definitely need to use this equation. Resultant force equals to forward force minus backwards force. Okay, so so I want to find the driving force. Okay, you should know the driving force is actually the forward force because the driving force is the one that causes the car to move forward. So this car is moving forward. So the forward force must be the driving force and the backwards force is the frictional force. So I will to rearrange this equation. Driving force will be equals to the resultant force plus frictional force. I bring this frictional force over plus frictional force. So my resultant force is from previously I calculated 4000 plus there is a frictional force of 50. Okay, so my driving force is actually 4050 newtons. Okay, you may scan the following QR code to work on your understanding of Newton's first law and second law. So let's do a very quick recap of first law and second law first. Okay, so it says that a force can have the following effects. It can cause an object to start moving, increase in speed, decrease in speed, or change direction. Okay, so it causes a force will causes an object to accelerate or decelerate. But sometimes forces acting on the body can be balanced. Okay, when the forces acting on the body are balanced, we say that the resultant force becomes zero. And Newton's first law states that if there is zero resultant force, an object will continue in its state of rest. If it's originally at rest, it will want to continue at rest, or its uniform motion in a straight line. Okay, if it's already moving, it wants to continue moving at a constant speed. Okay, if there are no net force or all the forces are balanced on that object. Okay, next, inertia, which is an extension of the Newton's first law. This reluctance of object to change its state of rest or motion due to its mass is called inertia. But sometimes forces acting on the body can be unbalanced. So when the force becomes unbalanced, there will be a resultant force. And Newton's second law states that whenever there is a resultant force acting on an object, the object will accelerate in the direction of the resultant force. And there is a formula for it. Resultant force equals to ma. Okay, whenever there is A, there will be F. there will be a resultant force. And the acceleration is in the same direction as the resultant force. But reminder, it doesn't mean my object move in the direction of the acceleration. My object can move in the opposite direction as the acceleration. Okay, next we move on to Newton's third law. Newton's third law of motion states that if body A exerts a force on body B, then body B will exert an equal and opposite force on body A. So these are actually called, one of the forces is called an action force and the other force is called a reaction force. We say that for every action, there is an equal and opposite reaction. Okay, so for Newton's third law, it is important to take note that the two actions and reaction pairs, okay, the forces, the force of A on B and the force of B on A are equal in magnitude, but they act in opposite direction. For example, I have a force that acts on the wall, okay, the boy on the wall, okay, so this force acts on the wall, and I also have a force, a reaction force, which is the force of the wall on the boy. Okay, for every action, there's an equal and opposite reaction. Let me show you some examples in real life.
Welcome to Moo Math and Science. In this video, I'd like to talk about real-world examples of Newton's third law of motion that states that for every action there is an equal and opposite reaction. The skateboarder, in order to do the kickflip over the bench, needs to first have his force go downward in order to pop the board upward. The jet moves forward because the force of the engine goes backwards. Look at these ladies paddling. They paddle backwards in order to go forward. This basketball bounces upward because it first goes down and the basketball court gives a force upward which causes it to bounce. Look carefully at this jellyfish. In order to move forward, it moves its body backwards, and the water has an opposite reaction and forces the jellyfish forward. Jumping on a trampoline is the same way. The force is downward, and then you have an equal force upward, which causes you to go up. And finally, look at this balloon. When the balloon hits the earth, it has an opposite force, which causes it to change direction and go upward. So there we go, some real-world examples of the third law of motion, which states that for every action, there is an equal and opposite reaction. Thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe and share.
Okay, let's move on. Okay, so I'm going to give you a few examples of Newton's third law. Usually when we talk about Newton's third law, we say that forces always occurs in a pair, and whenever we describe them, we always describe as force of A on B. Okay, we need to identify the two objects or two bodies that the force are acting on. So it's force of body A on body B, and the other pair will be the force of body B on body A. So you can see that the forces are acting on different body. One is on body B and one is on body A. They are exactly on opposite bodies. The direction will be exactly opposite of each other. But these two forces will be of the same nature. That means if it's one of them is a gravitational force, the other one must also be a gravitational force. If one of them is contact force, the other one must also be a contact force. So they are of the same type. Okay, but they are acting on different bodies and are in opposite direction, and they have the same magnitude. So we take a look at a few examples over here. I have a force when I have a baseball hitting the bat. I have a force exerted by my bat on the ball in order for the ball to move forward. Okay, so this is my two objects will be the bat and the ball. Force of the bat on the ball. So my action-reaction pair will be the force of the ball on the bed. So the ball will also exert an equal and opposite force on the bed. So this force is acting on the bed. So it's drawn like this. Okay, next, I have a girl who wants to throw the basketball into the net. So there is a force exerted by the girl's hand on the basketball to push this basketball up. Okay, the reaction pair will be the force of the basketball on the girl. Okay, so this one is on the girl. The red color arrow will be on the girl. And next, in order to move forward, in order to run forward, okay, the ground is actually pushing the girl forward. Okay, so the two objects is between the ground and the girl's feet. Okay, and similarly, the reaction pair will be the girl is pushing on the ground. Okay, the girl is pushing on the ground backwards. Okay, so these are action reaction pair. Next, more examples. Okay, whenever there are also other types of forces that you need to identify the bodies. So one very good example is the weight. I have a book on the table. There is a weight exerted on this book. The weight is actually caused by the Earth's gravitational field strength. So the two objects for weight is actually the Earth and the book. The weight over here is actually the force of the Earth on the book. Earth is pulling down on the book. So my two objects is not gravity and book, it's Earth and the book. Weight is caused by the Earth. Okay, it's always force of a body or an object. Okay, so the object is the Earth. The Earth is exerting a force downwards on the book. So that is the weight. So the reaction pair is not the contact force. Okay, a lot of students will give me, oh, there is a contact force on the book. Okay, but the contact force is exerted by the table on the book. So I cannot have weight, which is Earth on book, and contact force, which is table on book. Then both forces are acting on the book. These are not action-reaction pair. So the action-reaction pair is actually force of book on the Earth. So the reaction pair is on the Earth, not on the book for the action-reaction pair for weight. Okay, I repeat, this is weight, which is force of Earth on book. And then the reaction pair will be, again, gravitational force, but now is book on the Earth. Okay, if you were to draw a force diagram, it looks like that. It doesn't all occurs on the book. Next, okay, then let's take a look at this contact force. Okay, so this book is on table. There will be a contact force. As long as anything is touching a surface, there's a contact force. The contact force is 90 degrees to the surface upwards. So this contact force is caused by the table on the book. Okay, it's caused by the table on the book. Okay, then the reaction pair will be the book on the table. Okay, it's again a contact force, but it's on by the book on the table. So this force is acting on the table, and they are of equal magnitude. Okay, so both of them is what I just mentioned. Gravitational force is downwards, and then the reaction pair is upwards, and both of them are gravitational force. And then the normal contact force, both of them are also normal contact force. One is on the book, one is on table. Okay, so 4 characteristics of action-reaction pair. Forces are always occurs in pair. One is called the action, one is called the reaction force. Action-reaction pairs are always equal in magnitude. They are of the same size, okay, but they act in opposite direction. And they will always act on different body. So it's force of A on B, so it acts on B, and force of B on A, so it acts on A. So they will always act on different body. So what does it mean by it always acts on different body? It means that these forces cannot cancel each other out. Okay, you can only cancel each other out when the two forces act on the same body. So for example, I have a box A, I have 3 newtons acting on A to the right and 3 newtons acting on A to the left. So these two forces, 3 newtons are acting on the box, is on the same body. So they can cancel each other out to get 0 resultant force. But action-reaction pair always acts on different bodies. So they can never cancel each other out. Okay, and they are of the same nature. Okay, that's it for the first part.